First, let me say thank you to the authorities here for inviting me. It's a pleasure to be here today. And looking at this very broad audience, I'm reminded of an occasion back at UBC where I used to teach for many years when we brought Stephen Lewis to the Vancouver Institute on a Saturday evening. 3,500 people showed up to hear him. And he stepped up to the podium and he said, "I'm a socialist. And as a socialist in Canada, I am quite used to addressing mass gatherings of 6 or 7. I hear there are upwards of 3,000 of you here tonight. Thank you." I just thought that was kind of appropriate, counting the number of people here in the room. Well, I'm delighted to have an opportunity to speak to you about climate change, but what I want to do today is something a little bit different from the norm. I'm not just going to discuss climate and what's happening on the planet. What I really want to do is connect it to what's happening with respect to various influences on humanity. And I'll take us back now quite some time. Some of you may have recognized the name John Muir, who founded the Sierra Club a long time ago. And on July 27th of 1869, he was a young man in the Sierra Madre Mountains in California. And he wrote in his journal on that day something very similar to this, that when we try to pick out anything by itself, we find it hitched, and as he wrote on that day, hitched by 1,000 invisible cords to everything else in the universe. And then when he published his book, My First Summer in the Sierra, in 1911, he changed the quotation slightly and he simplified it and just said, hitched to everything else in the universe. He left out the 1,000 invisible cords. But it's the 1,000 invisible cords that I wish to discuss, at least in part today. So let me begin with perhaps the most iconic image in the earth sciences today. This is the concentration of carbon dioxide in the Earth's atmosphere, and most of you will be familiar with this curve. We call it the Keeling Curve in honor of Charles David Keeling, who was a graduate student at the Scripps Institution of Oceanography, and he decided in 1957 that he would build an instrument that would allow him to measure the carbon dioxide concentration in the Earth's atmosphere accurately. It had never been done on a routine, rigorous basis prior to that time. He built an infrared analyzer. He took it to a specially picked site, which was at Mauna Loa, high altitude, 3,400 meters. And the reason for that was that Hawaii is kind of like a barometer that sticks up in the middle of the Pacific Ocean. This is a well-mixed site, high in the atmosphere, far from cities, far from automobile exhausts, far from smokestacks. And so it represents a really nice, well-mixed indicator for carbon dioxide in the Earth's atmosphere. And in March of 1958, he began measuring CO2. Well, those measurements are continuing. They're made on a minute-by-minute basis now at Mauna Loa and many other sites around the world. And you can see what the progression looks like since the late 1950s. The little wiggles here, these are just the annual cycle, and I like to think of them as the breathing of the Northern Hemisphere. Because in the spring and summer, when all the leaves burst out and all the blossoms bloom and everything else and the trees start growing again, the CO2 concentration goes down by a few parts per million. Then along comes fall and the leaves fall down and photosynthesis pretty much stops in the Northern Hemisphere. And that's when the concentration goes back up as decomposition puts CO2 back in the atmosphere. So that's just the annual cycle. But look at that long trend. Now when I was born, the concentration was right here, 310 parts per million. This morning it's 397. That's an extraordinary change of about 40% in the lifetime of one baby boomer. And this is a very important point. To the best of our geological knowledge, Mother Nature has never, ever changed the concentration of a constituent in our atmosphere at that rate. Never. This rate is unprecedented, as far as we know, in the history of this planet. And it's a rate of change problem then that we're dealing with here. Because the planet has seen high concentrations of carbon dioxide in the past. 100 million years ago, they were a lot higher. What's happening now is that we're changing the rate so fast that systems are not going to be able to adjust. This is the CO2 molecule. 1 carbon and 2 oxygens. This molecule has an interesting behavior, and this is at the root of the issue here that we're discussing with our concern about global warming. And the behavior is quite simple. When visible radiation from the sun comes through the atmosphere, it passes right through a carbon dioxide molecule. It's short wavelength radiation, mostly white light. That radiation hits the surface of the Earth and warms it back up, and any warm surface will re-radiate heat away from it, but it's in a different form of radiation. We call it infrared, and it's long wavelength. And when a photon or a ray of that long wavelength infrared hits a carbon dioxide molecule in the atmosphere, that molecule does something really interesting. If this is the carbon and these are the two oxygens, and that infrared photon hits it, the molecule does this. It twists and stretches. And at particular wavelengths that are specific to carbon dioxide, infrared radiation is absorbed. And that molecule holds onto that. It does the twisting and the stretching for a few milliseconds, that's all. And then it relaxes back to that state. And when it relaxes, it re-releases that radiation. And yes, it could go up to space, or it could go sideways, or it can come right back at us. And some fraction of the infrared radiation that is trying to leave the surface of the Earth and get to space comes right back at us. And that fraction is growing. And it's growing because the concentration of this radiatively active gas is increasing in the atmosphere. Now, there's another piece to this, and I like to call this the squint test. And if you squint, if everyone squints at this now, you can see that this is curved. It's not linear. And in fact, it's accelerating. The curvature is increasing. We're putting more and more carbon dioxide in the atmosphere every day now, even though we've known for decades, that the planet is warming as a consequence of this activity. As a result, the well-known physics of carbon dioxide and that increasing concentration, the planet is warming up. This is the global average temperature change relative to the 3 decades from 51 to 1980, starting around 1880 and right up to the present day, to the end of last year. And you can see that in very general terms, we've been getting warmer. And this is both land and ocean, and it's scaled in terms of the difference from that base period, so it's shown as an anomaly. And we've warmed up since 1880 from about here to about here. It's about 0.8 degrees Celsius over the face of the entire planet. That warming, of course, is uneven. Some parts are warming very fast, like the Canadian Arctic. Others less fast. And there's variability in it. Lots of interannual variability year to year. Some of these are very easy to single out. 1991, Mount Pinatubo erupted. It put a vast amount, 20 million tons or so of sulfur, high in the atmosphere. That formed sulfate particles which reflected sunlight back into space, and the planet cooled a little bit. We've had La Nina years quite repeatedly in the last decade, so it's been a rather cool decade relative to what we might have anticipated with respect to this trend. Back in the early 1900s, we had a whole suite of volcanic eruptions. Mount Katmai in Alaska erupted in 1912, cooled the planet a little bit. And this big dip here, from 1945-ish up to about 1970, why did the planet cool then? Well, this was the post-war industrial expansion. And when the Second World War ended, we started to burn vast amounts of sulfur-bearing coal around the world to support the growth of industry, which burgeoned, I should say, through the 50s, 60s, and up to about 1970. And we were filling the atmosphere then with particles. White, shiny particles that reflected sunlight back into space. And then along came the Clean Air Act in the United States, the acid rain problem, the difficulty with acid rain in Northern Europe. And so various industrial countries got together and they passed legislation to clean up the atmosphere. That aerosol loading that was reflecting sunlight back into space and helping us stay cooler than we should have been, that ended in about 1970, and since then we've been seeing more or less the full expression of global warming. This will continue as long as the carbon dioxide concentration continues to go up. And we can see the effects of it all around us. You know, when you read in the pages of the National Post or something that the planet has been cooling for the last 16 years and therefore we don't have anything to worry about, ask them how this happens. If the planet is cooling, why in last September did we set an all-time record loss of Arctic sea ice? This is the annual progression in the Arctic as measured by satellite. And you can see that 2012, by the end of the summer, we set a brand new minimum record for sea ice aerial extent in the Arctic. The difference between the long-term average here from 1979 to 2000, which is shown by the gray line, and the 2012 minimum, that's about 4 million square kilometers. That's equivalent to the area of British Columbia, Alberta, Saskatchewan, and Manitoba all together. That's the difference from the longer-term average. We're losing sea ice at a frantic pace now. Now to put this change, this rate of change problem that we're dealing with in a better context, we need to always think in long time scales. And human beings aren't very good at that. We tend to think maybe about as far as our grandchildren, 2 or 3 generations. We don't tend to think much beyond that. But if we look where we are in terms of the temperature, we're sitting here today. If we go back in time, well, of course, the last 100 years are almost vertical on this 11,000 year or so time scale, or 12,000 years. If we go back in time, it was a little bit warmer here in what we call the Middle Holocene, about 6, 7, 8,000 years ago. Of course, as we go farther back in time, if I had drawn this graph farther on, it would go right back into the last ice age when it was 5 degrees colder globally. But it did warm up a little bit, several thousand years prior to now. It cooled during what we call the Little Ice Age. And then along came industrialization, and here's where we are today. We're above anything that we've seen in the last 11,000 years. And the trajectory that we're on this time scale, is vertical. This is our rate of change problem. And look at how far out of context we will be by the end of this century at the rate we're now going. Somewhere between 2 degrees warmer and maybe as much as 6 degrees warmer globally. We can start to see the effects of this now. This is no longer in the realm of supposition. This is now in the realm of reality. I love this diagram. This was published 2 years ago in the journal Science. What's shown here, there's 511 vertical lines on this graph that are compilations showing the summer temperature, June, July, August, those 3 months, across the European landmass. This is just land, and scaled in terms of anomalies, that is, changes relative to the long-term mean. So the anomaly is along the bottom, the frequency distribution goes up the vertical axis. And there's 511 summers of data on here. And they describe this distribution here in general terms shown by the black line. But let's pick this apart a little bit. Ask yourself, when was the last really cold summer in Europe? Really cold summer within sort of recent human memory. So you look at this side of the graph, and what do you see? 1923. That was the last cold summer in Europe. And then you ask the opposite question. When were the last warm summers in Europe? Well, 2010, 2003, 2002, 2006, 2007. They're all sitting way out here. This one, for those of you that like statistics, that's 4 standard deviations from the mean. That's so far removed from our human experience that it's just absolutely unanticipated. No one anticipated that you could have a summer sitting that far away from the anticipated distribution over several centuries. And it's going to get worse, because what we're doing in terms of adding CO2 to the atmosphere is we're pushing climate into a new state that is skewing the distribution in the direction toward the right. Now, that doesn't mean we're not going to have cold summers. That distribution is still rooted over here on the left-hand side of the tail. And so we will get the odd cold summer in Europe. What we will see, though, as time marches on, is that we're going to have an increasing number here of very hot summers. And these have direct implications for humanity, the scale of which is quite shocking, actually, when you start to look at it. The United States last summer, in fact, in the calendar year 2012, went through an extraordinary heat wave. It was, by any yardstick, the warmest year in recorded American history since thermometers were invented. And if you look at how that year stacks up in terms of its previous record years, this is for the lower 48 states now, the contiguous United States. Here's where 2012 is. Now this is in Fahrenheit, 55.3 degrees Fahrenheit. But look at the previous records. The previous hottest year in the United States was 1998. That was the very famous mother of all El Niños year, when the Pacific Ocean in the equatorial region was extremely warm, radiated a lot of heat into the atmosphere, and until very recently, 1998, was the warmest year globally. It was also, until very recently, it was the warmest year in the United States. And it just barely edged out 2006, and then of course the Dust Bowl year of the mid-1930s was the previous record, and so on. But look at the step function there. This was, again, an extraordinary event, unprecedented in historical experience. Now this particular event has had all kinds of profound implications for the globe, more than just the United States. It's been associated with an ongoing drought, and that drought started about 2 years ago. First appeared in the late winter of 2011, centered here in the south, particularly over Texas. By September of 2011, it got really intense, and the summer of 2011 was the hottest summer in Texas history. It had all kinds of very serious implications for agriculture. Those of you who buy peanut butter will recognize that the price of peanut butter took off in the fall of 2011. And that's because the peanuts that are used to make peanut butter are grown in Texas and in Georgia. And they were both hammered by the drought. And the peanut plants could not grow, and the yield was way down, and as a consequence, the price of peanut butter shot up by about 35 to 40% in October of 2011. Well, that drought, which has started back 2 years ago, here's where it is 2 days ago, 3 days ago. It's still in place. It's afflicted a very large part of the United States. And this dark color here, this is exceptional drought. And I like to describe that as being beyond extreme. It's beyond extreme. This is very rare to have dry conditions that are so powerfully dry as they are now in the United States. Here's the forecast up to the end of June of this year. It was released yesterday. And that forecast shows that the drought is very likely to persist over most of the southwestern side of the United States. We might see some slight improvement along the edges here coming up through Oklahoma and Kansas, but only slight improvement. And it's imperiling, for another year, it's imperiling agricultural production in the United States. It's likely to get worse as time marches on. Our computer models suggest that particularly in the southwest, we are going to see a rather remarkable number of years with temperatures above 100 degrees Fahrenheit or 38 degrees Celsius, depending on what we do as a human species, depending on whether we start to limit our emissions of carbon dioxide or we continue on the path that we are on now. If we stay on this path, and I should make the point that we're actually exceeding this emissions scenario. This was published in 2009. We're actually exceeding the higher emissions scenario that was included in this compilation. So if that's going to be the path that we continue to take as a human species, we will see something on the order of 4 months per year in Southern California, Arizona, and down here in southern Texas, where the temperatures on a daily maximum exceed 100 degrees Fahrenheit. And the implications for that are extraordinary, not just for agriculture, but things like electricity demand. How are we going to produce the power to provide the air conditioning that will allow human beings to continue to inhabit these regions? This is actually a huge issue, and it's already becoming a big issue in Texas. In terms of farming potential in the future, if you look at the soil moisture that is predicted to be in place going forward in time, by the end of this century, based on a suite of 14 different model outputs. This was compiled by Agu Dai, who's a very bright young climatologist in Colorado. I published this last August. And what he's looking at here is a model output based on temperature, wind regimes, evaporation rates, and he's compiled it in terms of what's called the Palmer Drought Severity Index. Essentially, that's a measure of soil moisture. And the best way to look at this is anything with the colors that are sitting down here at this end represent extremely dry soil, characteristic of desert soils. Where is that going to happen? According to the model projections, and again, of course, these are scenario dependent. It really depends on what we do as a human species with respect to our CO2 emissions. But look at the circum-Mediterranean region, right up through France and the Balkans. Look at the Amazon basin drying out. Southwest United States will have severe soil moisture deficits. Australia will have severe soil moisture deficits. Parts of Africa will have severe soil moisture deficits. This is not good news. This is extremely worrying for the future of agricultural production that will feed a much larger population likely by the end of this century. Now we're starting to see the leading edge of the biting impacts of these things are starting to appear pretty regularly now in our media channels. Now I'll just draw your attention to a few. There's a big financial hit because of the drought in the United States. It's a record bill of $16 billion in crop insurance because of the low yields last year. But there's an irony in that. The low yields have caused the price to rise. And so the net farm gate returns to farmers, or many farmers, are actually gone up. Their yields are down, but they have more cash in their pocket. This is a perverse, rather, result. Although the implications go way beyond just what happens to farmers' wallets, and I'll mention those in a moment. We're not starting off in a good way in California this year. January and February were notched the driest 2-month period in recorded history across the northern Sierra Nevada. This is bad news for next summer's irrigation requirements for the Central Valley in California. And if that drought does not break this month, they're going to be in real trouble. And it's already March 22nd, and the drought has not broken yet in California. So it looks like we're going to have a very, very bad summer in terms of irrigation requirements, meeting irrigation requirements in California in the summer. Drought stokes water fights. This is in the Wall Street Journal, January 16th of this year. Texas asked Supreme Court to force neighbors to slake part of its growing thirst. And when you read these stories, what's happening here is that the state of Texas is suing New Mexico and Oklahoma over water rights. Now this is surface drainage, and they're demanding a bigger share of the surface drainages that are originating in these other states. There's a wonderful irony in this. The governor of Texas, what's his name, David?
Rick Perry.
Rick Perry. Rick Perry is a global warming denier. And his state, more than almost any other state in the United States, is in the front lines right now of suffering from what's been happening with the whole global warming phenomenon. He continues to have his head buried very deeply in the sand. And every day that sand is getting drier. And I don't know how long he can continue to be a denier in the face of the evidence that's been mounting. But nevertheless, what we're starting to see now is interstate legal suits erupting in the United States. This is not the only one, based on water shortages. This is going to get worse as time goes on. In fact, Texas, if you look at where they're likely to be going in the future, this report came out in January of 2012 from the Texas Water Development Board, commissioned by Governor Perry, in fact, to explore where Texas can get more water. And what this board came up with was that in the event of severe drought, the state faces an immediate need for additional water supplies of 3.6 million acre-feet per year. That unit doesn't mean much to a lot of people, so I did a quick calculation. That's 15 days of average Fraser River flow. That's the shortage of water perceived in Texas. An extraordinary volume of water that are going to be short. Planning groups were unable to find economically feasible strategies to meet over 2 million acre-feet of annual needs. Economic losses will be in big numbers as time marches on, based on their lost agricultural productivity. In 2012, the state of Texas lost $7.2 billion worth of farm gate receipts. $7.2 billion of farm gate receipts directly in one state from the drought that's ongoing. Now you might say, well, you know, they can just mine groundwater. And maybe they could in the past have mined groundwater, because part of Texas, right down through the panhandle here, is underlain by the well-known High Plains Aquifer, also known as the Ogallala Aquifer. And that aquifer runs from South Dakota right down into the heart of Texas. It's essentially a big, thick lens of gravel that was produced by millions of years of erosion of the Rocky Mountains. So this really runs down the eastern side of the Rocky Mountains. In 1850, that aquifer contained a volume of water equivalent to that in Lake Ontario. And then along came the settlers. And those of you who've watched John Wayne movies will know that on the horizon in every John Wayne movie there's always a windmill. Now this is in the 1860s or 1870s. And the windmill is turning lazily. And that windmill was not generating electricity. It was pumping water out of the ground. And it did that, or was able to do that, because the water table was relatively shallow. And that water table now is down very deep. This goes up to 2001, so it's already way out of date. It's the best data set I could find, though. The decline in the areas that are shown in red here is more than 150 feet. Now that's since the pre-industrial time, about 1850. The authorities in the U.S. Hydrological Service suggest that these regions right here in southern Kansas and down through the Panhandle have maybe 20 years of water left. That's it. 20 years of water. They've been supporting a large part of the agricultural enterprise in northern Texas, Kansas, and Oklahoma through mining groundwater. And it's a finite resource. It's not being recharged anywhere near as fast as it's being used. And so a few decades from now, Texas is going to face even more severe water shortages than they already are. So just think about continued warming, soil moisture deficits growing, CO2 continuing to go into the atmosphere because human beings can't seem to get their act together. And what does it mean for the agricultural production of the breadbasket of North America? This is not good news. So that part in particular of the aquifer is very susceptible then to depletion within the lifetimes of most of us in this room. Now I want to say a few more words about this particular event here, the 2010 event. This was an extraordinary thing that happened there. We had what's called a blocking high that sat parked over Moscow through July and August, 62 straight days in fact, in 2010. In this region, the temperature records were just simply blown out of the water. And they were setting records. This is the temperature scale here in degrees Celsius, departure from the norm for the month of July. The red color here is 6 to 7 degrees above the norm. Now, 6 to 7 degrees Celsius warmer than normal is a big, big step. And yet, that's what was characterizing much of Western Russia. This had all kinds of implications for humanity, some of them global, some of them more regional. They had 11,000 excess deaths in Moscow in the summer of 2010. 11,000. The normal mortality rate is about 14,000. We had 25,000 Muscovites die. They died from heat prostration if they were old, elderly, and vulnerable, or those who had pulmonary dysfunction of various kinds, emphysema and so on. They died because they had difficulty breathing in the air, which became filled with smoke because there were so many forest fires broke out in Western Russia. So there were 11,000 excess deaths, and the global implication is shown here on the right-hand graph. As we came into the heat wave and the drought that was associated with it, the Russian wheat crop withered on the stalks, as it did in the Ukraine. The speculators moved in. Many countries went out and started to stock up on wheat because they saw that the yields were going to go down. And the price went from around $180 US per ton here at the end of June or so to about $270 a ton within 5 weeks. That caused ripples around the entire world. Russia closed its borders to wheat exports at the end of July of 2010. And immediately the market responded by driving up the world price. And it wasn't just wheat that got hit by this, because wheat is one grain and it's substitutable by other grains if, for example, you're feeding livestock. So it had an impact on all other grains, corn being one of them. And when we look at the price of corn over the last nearly 100 years now, you can see that it was gradually creeping up until about 2005, and then it's gone through the roof. It set an all-time world record last August of $8.49 a bushel. As of last month, it was down to $7.65, but that's still much, much higher up here than it has been traditionally. Now, there are a number of factors that are feeding into this, and climate change is only one of them, although it has indirect links, as I'll show. This comes back to the 1,000 invisible chords of John Muir. If we expand the right-hand side, if I'll take this latter portion of the curve here and now just expand it, and scale it in terms of the overall food price index, of corn being a big part of that, but not the only part, the price of food didn't vary an awful lot through the 90s and into the mid-2000s. And then along came 2005, 2006, and away it went. It recovered a little bit in 2008, and then away it went again. Now, what caused these two big spikes? Well, the first one was an indirect influence of climate change. George W. Bush, following on from Bill Clinton, recognized that the United States was beholden to foreign oil suppliers, and therefore that they should try to wean themselves from foreign oil. This was a very noble objective. This was a good idea that he had, and it started with Bill Clinton. And so in 2005, George W. Bush signed into law the Energy Policy Act. And that set a renewable fuel standard that required ethanol to be produced, a fair bit of it, 28 billion liters, by this last year, 2012. That didn't go far enough in the view of many, and so they passed a new law in 2007. This one, I like the title of this, the Energy Independence and Security Act. The idea was to wean themselves progressively from imported oil, and that increased, more or less doubled the target to 57 billion liters from 2022. But the substrate to produce that ethanol was corn. And the reason corn is chosen is because it's rich in sugar. Corn syrup, for example, is easily made from corn. And sugar is easily fermented into alcohol, or ethanol. It's a good substrate to make ethanol. And so now 40% of United States corn production goes directly into the ethanol stream. 40%. And it's subsidized. They get 45 cents a gallon for each gallon of ethanol that's produced. But that explains only this peak. Those were those ethanol acts that did that. And then the market recovered when more corn got planted and so on. So what happened here? This second peak, that's 2010, 2011. Well, that's the climate change peak. That was the Russian impact, but it wasn't just the heat wave in Russia, because also in 2010 we had record rainfall or near record rainfall in Saskatchewan, Manitoba. Our wheat yields were down in Canada. You might remember that at the same time the drought was underway in Russia, in September, just immediately after that drought, the Indus Valley got flooded with unprecedented monsoon rainfall. You might remember the images on the nightly news showing at one point 85% of the Indus Valley region was underwater. It was extraordinary floods. Again, record in extent. Queensland in Australia, record flooding again, damaged their sugarcane harvest. So the price of everything started to rise as a consequence of these insults. What's happened with corn, though, is that because of both the drought in the United States in starting in 2011, continuing on today, plus the diversion to ethanol, the tons of corn that are available now for export are plummeting. And the warehouse stocks of corn in the United States are plummeting. Now, the consequence of this is very much global in extent, because the United States is by far the world's largest exporter of corn. And with the Green Revolution that commenced in the 60s, then the United States started to produce a vast amount of corn for export. And over much of the time since the 1960s, they've commanded about 40% of the world's market for corn export. That's now sagging downward. No other country had anywhere near the clout in the corn market the United States had. Now, export's one thing. But I always ask, you know, if somebody's exporting, I turn the coin over and I say, okay, who's importing? Where's that corn going? And this is the interesting part of that phenomenon. A lot of it goes into Eastern Asia. A fair bit of it goes into the Middle East and Northern Africa and other developing countries. And if you take those two pieces together, the red and this olive color together, that's a big part of the world corn imports. The countries that are involved here are countries like Malawi and Kenya and Chad and Libya and Egypt and Tunisia and Morocco and Saudi Arabia. Most commentators are now saying that this decline that we see here has had such a profound effect, along with the price rises that we've seen on the global commodity scale, that was a fundamental driver of the Arab Spring, of the revolutions that we've seen in so many of those countries. Because the price of food dramatically rose in those countries over the last few years. They had bread riots in Cairo, for example, that helped to influence the decision to get rid of Muir. Now I want to end up with a connecting the dots explanation here, because I haven't done that yet. And I want to tie this into what's happening in the far north. The loss of summer sea ice that I showed you so earlier in the Arctic is extraordinarily important, and there's a good emerging physical explanation for this now. What's shown here in white is the Arctic sea ice extent at that record minimum on about September 23rd of last year. The orange line is the long-term normal expectation for late September in the Arctic. And that's the 4 million square kilometers here in that arc around it that's missing, or went missing last year. What happens is that the sun shines down on the top of the Earth in the summertime. This is a mirror. When the sunlight hits it, it gets reflected back into space. 85% of the sunlight that hits that white surface goes back into space. But if we remove that white surface, and instead have the sun hit the dark ocean, 85% of that sunlight is absorbed by the ocean. The Arctic Ocean is warming up. We can measure this. It's warming up. Now along comes the end of September and it gets cold again. The Earth is tilted away from the sun and we go into darkness at the North Pole. And what happens? Well, there's all that excess heat that's been added in the late summer into the Arctic, and it re-radiates back into the atmosphere. And it warms the Arctic environment more so than it did in the past. And this is, we call this Arctic amplification. The Arctic is warming. Recent research, and this is very recent now, March and October of last year, by Jennifer Francis at Rutgers, and PICS, Pacific Institute for Climate Solutions, brought Jennifer to Victoria and Vancouver in February. You may have possibly have heard her on the radio, or saw the news reports in the media. And a group at the Potsdam Institute, Vladimir Petukov and Stefan Ramsdorf and others, just 2-3 weeks ago, suggested that the release of accumulated heat to the Arctic is weakening the equator to pole temperature gradient. In other words, think of 30 degrees Celsius at the equator, 0 at the pole, let's say minus 20 at the pole. That's a 50-degree difference. Now it's only minus 15 at the pole. So the gradient has gone from being a 50-degree difference to a 45-degree difference. That's what's happening. The heat that's released and the weakening temperature gradient weakens the jet stream, and I'll explain this in a moment. So what's happening with the jet stream is we're seeing it move in terms of phase speed more slowly across a greater latitudinal range. And so we're getting very slow progression of high and low pressure cells now, and you can think of them as being stalled weather systems that are sitting parked. And they'll be parked over the big chunk of the United States, for example, a heat wave, and it doesn't move. Or it might be a low pressure zone that gets parked over Pakistan and doesn't move and leads to huge flooding. So here's the simple-minded physics of this. At the equator, or at least in the low latitudes, we have a column of air, which of course is warmed by the sun because there's lots of sunlight down in the lower latitudes. And that column of air is quite thick. The air rises and cools, and by the time we get up into the northern hemisphere, of course, where it's cold, that same column of air is quite thin. So there's a hill, a slope. It's a physical slope in the atmosphere. And so as this air cools, it flows down that slope. And as it flows down that slope, of course, the Earth is spinning underneath it. And that's what leads us to the jet stream. The Earth is spinning away from that air, and so we get the jet stream forming. Well, what we're doing is we're warming up this region disproportionately to here. And so the column of air is expanding here. Our slope isn't as profound as it used to be. And the result is that the jet stream, just like a river that's flowing down a steep slope, it'll go straight down a steep slope. But as soon as it hits a coastal plain, it'll start to wander. It'll start to meander. It has less energy essentially driving it. And that's what we're seeing now. These are real data. This is from the Pederson paper that was published a few weeks ago. This is now looking at essentially an equivalent of the jet stream. We call them planetary waves, or Rossby waves in the technical jargon, in the mid-latitudes here between about 60 degrees north and 37 degrees north in the northern hemisphere. Here's the normal distribution of wind speeds in the northerly-southerly direction. So just wind speeds north and south in what we call a normal year, July of 1980. The jet stream sort of looks like this. The warm colored zones here are warm air carried to the north. The cooler zones are colder air coming from the south and from the north. So that's kind of the normal progression of the jet stream. Here's North America. Winnipeg is right here. Vancouver's right here. And that's what we would kind of normally expect. But here's what's happening. This is an extreme case. The July 2011 heat wave that sat parked right here over the heartland of North America. And this is what the jet stream looks like now, or at least in an extreme year. It is swinging farther to the south and farther to the north. And it's no longer, the phase progression is such that this wave, if you think of this as a train, this train would be moving across the northern hemisphere like that. What's happening now is that this train is moving much more slowly. And so a heat wave that's bringing up warm air from the south is just moving extremely slowly. And so instead of 3 days of heat wave, we're now seeing maybe 11. 13, maybe even a month sometime. This won't happen every year, but what we have done is we have loaded the dice so that Mother Nature now is going to be more likely to establish this kind of a situation more frequently than we did in the past. So here's the pen that connects those dots. It comes back to what is driving global warming. Our challenge is to change the path of that curve. We need to bend it. So instead of keep going up at an ever-accelerating pace, we've got to start it going the other way. And this is a challenge of unprecedented proportion for humanity. Absolutely unprecedented. But we can do it. And I don't want anyone to leave this room with a black cloud over their head saying we're all going to hell in a handbasket, because it's up to us. We can change the way we do things. We do have choices. For example, if we look at the world's electricity supply, 40% of the global electricity supply comes from burning coal. 40%. 1 kilogram of coal gives us 1 kilowatt hour of electricity. But, sorry, one kilogram of carbon dioxide is produced per kilowatt hour of electricity produced by burning coal. Well, what if we switch to natural gas? We cut that by a factor of 2 instantly. If we took our coal-burning power plants around the world and instead installed natural gas burning systems, for the same amount of electricity produced, we only produce half as much CO2. And then if we go to solar photovoltaic, we can cut that by another factor of 10. Now we're a factor of 20 ahead of coal. If we go nuclear, we can take another factor of 3 in there. Now we're a factor of 60 better than coal. We have these choices in front of us. Our challenge is to accept them and go for it. It's starting to happen. Here's an example of a concentrating solar power system that's under construction now near Las Vegas, right down here on the California-Nevada border. In this case, what we're looking at is towers that have water-filled boilers on top, a whole number of mirrors that are focusing sunlight onto those towers. They superheat the water to many hundred degrees Celsius. That's used to produce steam, which is run through turbines to generate electricity. The cost is about $6 a watt or a little less, which actually happens to be about the same cost as the Site C Dam in British Columbia. So this is cost effective in terms of competing with new hydropower in British Columbia. It's happening now. I'm going to wrap up with a quiz and then a couple of last points. And I want to ask who said this, or these 2 quotes. Greenhouse gas emissions and global warming are among humanity's most pressing concerns. There is a hint here. Societal expectations on climate change are real, and our industry is expected to take a leadership role. This same individual said that we know that pumping oil out of the ground does not create many jobs. Take note, does not create many jobs. It does not foster an entrepreneurial spirit, nor does it sharpen critical faculties. Who said that? Was it Stephen Harper? No. Was it Tom Mulcair? No. I'm going to give you the answer. It was the Saudi Arabian oil minister last year. Now this is interesting because this particular speech that he gave was a very important speech that he gave at Chatham House because it represented a wholesale change in thinking in the Middle East. And that change in thinking is now rippling across the whole region at a rather furious pace. Saudi Arabia is now intending to invest, in fact it's underway now, over $100 billion in solar voltaic power. And this is from last May when they first announced that, and then on September 23rd, now they're starting to fight over who's going to take the leadership role within Saudi Arabia. Mecca wants to be the lead city. They're going to put in 41,000 megawatts of solar voltaic capacity using silicon PV cells or photovoltaic cells. And to put that in perspective, our entire grid capacity in BC is 12,000 megawatts. They want to do this by about 2030 or so. They're now underway. Good for them. One way to get there, one way to drive humanity more toward that is to start to recognize the fact that we cannot keep using the atmosphere as an open sewer for our emissions. We cannot. We need to put a price on discharging those emissions to the atmosphere. The best way to do that is with some form of a carbon tax. And in fact, our captains of industry in Canada are now asking for it. Rick George, when he was still CEO of Suncor 2 years ago, said he wanted to see a $40 a ton carbon tax nationally in Canada. Lars Backer, last March, a year ago, in Vancouver at a public speech, said that Statoil Canada, which has a big piece of the oil sands, now uses $50 a ton in all of its business planning as a shadow carbon tax. And he said on the basis of that $50 a ton CO2 emissions tax that we include in all our plans, we have not rejected a single capital expansion or investment in Canada. But last September, Lorraine Mitchell-Moore, president of Shell, said that she wanted to see a significant price put on carbon and that Shell will not invest further in carbon capture and storage until that price is put in place. When I asked her communications people what did she mean by significant price, they intimated that something in the $60 to $75 range would be acceptable to Shell. So that's what the captains of industry in the oil patch in Calgary are asking for. Here's what our Prime Minister said on September 17th in the House of Commons in response to a question from Thomas Mulcair. And you can read that. And this, I think, nicely encapsulates where we are now in Canada with respect to facing the future in an appropriate way. So I will end by suggesting that yes, there are 1,000 invisible cords. We are hitched to everything else in the universe. And in climate, carbon dioxide is one of those cords. It is invisible, but it is also very primary. We need to do something about it. John Muir had it right. Thank you.